So, a recitation on Monday was a lovely tour through sustainable materials. I encourage watching that if you weren't there, on how to produce locally materials for your lab rather than sourcing them at a distance. No recitation coming week, following week, important one on machine building. Today's electronic design. So you've used electronics, now finally we start designing it. Assignment is going to be designing your own microcontroller board. And so to do that, we need to cover two things this week. One is an introduction to the components, and then second is an introduction to the design tools. And this is sufficiently specialized that the design tools we're going to use are for electronics rather than the general purpose CAD. So first part is components. As usual, each week the top is linked into inventory. And so here's a sea of components. This is a link to a class I teach on the physics of information technology where I explain what's going on inside them, but I won't cover that today. But if you want to know more. So first is URL was rejected. Oh, I hope there isn't a DigiKey issue. Okay, no, that was a specific. Oh, okay, I see. The I need to here. I'll make a note. I need to fix the ribbon cable link. Let me do it this way. Okay, I'll fix that link. So this is really handy stuff. It's multiple wires in a bundle. They're colored so you can tell them apart. You can use them together as a ribbon, and we have connectors where you use all of them together, but you can also peel them apart and get one or as many wires as you need. The cable is rated by the pitch, the spacing between the wires, and the AWG. AWG sets the diameter of the wire, and then you'll find charts like this that relates the AWG to the current, to the resistance of the wire, and then to the current you can carry in the wire. So less current, you can use finer, smaller wires. And so in the standard inventory, we don't have reels of hookup wire. We just have a big reel of the ribbon cable, and you can pull off from that however many strands of wire you need. Then these are what are called IDC connectors, insulation displacement connector. And so we have these in many different sizes. And if you look there, what's going on is the bottom of the connector has a feature that looks like that. And then there are multiple ones depending on the number of pins. And then in comes the ribbon cable with the wire inside. Then there are special tools you can use, but we just use the housing. If you compress it, what this does is it pushes the wire down into the fingers, and the fingers make contact with the wire. So it's called insulation displacement. And so what it lets you do is slide the ribbon cable in, squeeze it down with a vise, and then make contact to make the connectors. The one note is if you only squeeze it down a little bit, the connection isn't reliable. You need to make sure the wire gets pushed all the way in, and then it makes a good connection. So that's what we use to go from ribbon cable to a connector to make multiple connections. You've already seen buttons. This is a classic button. The button electrically is normally open, and then when you push it, it closes it. Internally, if you look on the back of it, there's a line, and so there's 4 pads, and they're connected in pairs, so you can connect to either one. And then the switch that's normally open is a push button, and it closes when you push it. So that's a button. This, on the other hand, is a slide switch. So it has 3 pins, again, surface mount part. And there, the switch comes in, and it can be in one of 2 positions. But it stays where you keep it. So you can use this, for example, as an on-off switch or as a mode switch, because it stays on either side wherever you push it. So that's a slide switch. Here's a classic resistor. And again, these are all surface mount. We're not using through-hole components, which are largely obsolete except for special things that need mounting. So a resistor, you draw like that. That's the US version. In Europe, you can see it drawn like that. And there's current, voltage, and resistance. So the current flowing through the resistor equals the voltage drop across it divided by the value of the resistance. And so we use resistors. Most common use is to limit current. And I'll show you an example of that shortly. Resistors have funny values that have evolved historically. And so you'll see those when we start getting into the example circuits. Then a capacitor looks like this. And the capacitance is charge over voltage. So the capacitor stores charge and then has a voltage drop. And the relationship between charge and capacitance is voltage. So for the resistor, IR equals V. For the capacitor, CV equals Q. Or if you do the rate of change, I'll take what's called a derivative, which measures how fast something changes. The rate of change of the voltage equals the current. What that means is a capacitor stores charge, a DC signal can't go through, but an AC signal can go through a capacitor. So we use them as filters, and we use them as local ways to store charge. And so here's a capacitor. And so commonly, you'll see, for example, when we have a microcontroller, we'll put a capacitor next to it between the power supply and the ground. Or I'll talk about this when we have voltage regulators. And this stores some charge by a component to help supply it when it needs it, and it helps filter noise around it. This is an unpolarized capacitor, which means the voltage can go in either direction. Then there are polarized capacitors, and this is an extreme one called a supercapacitor. So supercapacitors, so polarized capacitors, you can draw asymmetrically, and there can be a charge sign. On those, you can only have voltage in one direction. And in fact, this one is limited to a fairly low voltage, 3.8 volts. But the last capacitor I showed you was a microfarad. that's 10 to the minus 6. This one is 10 farads. That's 10 to the 7, 1 followed by 7 zeros bigger. So a huge capacitor. So it only stores voltage on one side, and it's a fairly low voltage, but it's a huge capacitor. And so these are really useful as kind of micro batteries. You can charge them very easily, and they provide short-term power for something you want to work like with a battery. So those are capacitors. Crystals tell time. You can think of them as a capacitor, but inside the crystal, there's a piezoelectric material, which means the voltage makes it flex, and when it flexes, it makes voltage. And in terms of frequency, if this is the frequency, there's a resonance at a very sharp peak. And so we use these to tell time. They give us very accurate time references. Many of the processors we use don't need these. They have an internal source of time, but it's not as accurate as the crystals. The crystals can be parts per million rather than a fraction of a percent. This is an inductor. So for an inductor, you draw it like this. And for the inductor, the voltage across the inductor is L di dt. So it's backwards. For the capacitor, C dV dt is I. In the inductor, it's in the opposite side. Di dt L is V. What that means is the inductor lets DC through, but it doesn't let high frequency through. And so we can use those on, for example, power lines to block noise as a common use for inductors. But it's likely you won't need one. You won't encounter one. Diodes we make a lot of use of. So this is a diode. It has two sides. There's an anode and a cathode. And if you look at the voltage across a diode versus the current, in an ideal diode, it looks like this, meaning current goes in this direction, but it can't go in that direction. And you can remember the direction because think of the symbol as like an arrow. The arrow points in the direction of current, and it goes in alphabetical order. It goes from A to C. Let's see. There's a question about derivative as fractions. The reason why, this is way beyond the class, but the reason why derivatives make sense as fractions is they really are. That in defining the derivative is you can define it as a ratio of the size of change of these. But that goes beyond what we need to know for the class. So diodes block current. And so this is an example of a Schottky diode. And it's very important that one side of the package has a line. And the line on the package, if you look at the physical package, there'll be a mark or something on one side, and that corresponds to this side. So current goes in the direction of that. So a common use for a diode is to protect a circuit. If you have a diode on the input, and then this is your circuit, current can flow in, but if you connect the power backwards, you can't kill it, is a common use for a simple signal diode. This is a special diode called a Zener diode. And it looks similar, but what's going on there is the Zener diode you draw with a wiggly line. And if you look at its current voltage curve, it looks the same in the forward direction, but in the backward direction, there's a sharp drop off. And so a common use of Zener diodes is clipping a voltage so it can't pass beyond that. Now, an actual diode doesn't quite look like this. An actual diode, it looks roughly like this. So this is called the diode drop. And so there is a small voltage drop across the diode, like 0.6 volts is typical. This little quadrant is where solar cells work. That's where you make power. And then the reverse direction, you can actually use it as a sensor, that this can be sensitive to temperature and light for what's called the leakage in the reverse direction. Then we get to LEDs. So this is a light emitting diode. And it looks like that part has to be updated. So I'll change that to a current part. So for the LED, it's a diode and you draw it with a wiggly line coming out, and current comes in and light comes out. So the LED is specified by the voltage drop across it, the current that it can handle, the range of angles it comes out, the wavelength of the light, and in this case, this is red, and then the amount of light, the brightness, how much, this is how much light it can produce. And this is a small amount. This is enough just for an indicator diode. Now, a key thing in diodes is LEDs is if you take the LED and you connect it to your power supply like that, if this is a hefty, good power supply, your LED will explode, which is bad. That's because we haven't controlled the current through it. So you never do that. You always take the LED and you have a current limiting resistor. So if this is, say, 5 volts here, the diode drop for the LED, say, is 1 volt across it. And so if you have a 1K resistor, remember current is voltage over resistance. And so if we have a 1K resistor, it means we'd be putting 4 milliamps through the diode, which is a typical number. So you always have a current limiting resistor going to an LED to set the current through it. There, when we get to output devices, there's other ways you do that for very high power LEDs, but for small LEDs, that's how we do it. The other thing is the package. So all the components I've shown you are 1206. 1206 corresponds to in the width and the height of the package in English unit in tens of thousands of an inch. And the reason we're using 1206 packages is a typical size for the small end mill we use is 1/64th. And if you have a pad for a 1206 package, you can route a trace underneath it and with a 1/64th inch end mill. So this is a slightly large package size. Dense circuit boards use smaller components. We use that size because it's easier to solder by hand. And also you can route it, you can easily route a trace under it when you're laying out the circuit board, which I'll talk about in a little bit. So that's LEDs. Then we get to transistors. So a bipolar transistor looks like this, and it creates a ratio between current this way and current that way. We're not going to be using those. They're always consuming current. We're going to be using MOSFETs. And this is one of the best parts in the class. So many of the things I said you'll be able to do come from MOSFETs. So that's a MOSFET, one way to draw it. There's a gate, there's a source, and there's a drain. And think of the MOSFET roughly as a variable resistor controlled by the gate. So RDS is the resistance between the drain and the source. And well, let's go to an actual data sheet. So if we look at the data sheet for this MOSFET, so this is in a SOT23 package about the size of a grain of rice. And if we go to the data sheet, this is showing the voltage between the drain and the source. This is showing you the current. And then each of these curves is varying the gate voltage. And so when the gate is low, it doesn't conduct. But when the gate is high, it's a good conductor. And so it's like a resistor you can turn on and off. Let's see, there's a question about the value of the current limit resistor. The current limit resistor isn't, let's see, two questions. The current value of the resistor depends on the application. It depends on your power supply and the source. There isn't a fixed value. To Enterprise Fab Lab, right now I'm giving you a tour of parts. I've linked, these are two dear colleagues. The Art of Electronics is a fabulous Bible of learning about electronics. And then I'll talk about tools you can use to play with the components. So I'll come to that question in a little bit. So the MOSFET is a variable resistor, but one of the most important parameters is RDS, the resistance. And for a good MOSFET, it's on the order of milliohms, a thousandth of an ohm, which is a tiny amount. And then the other parameter is the current, and this one does 1.7 amps. And it does it up to 30 volts. So this little tiny part can switch enough current to drive a big machine tool. So we generally don't vary the gate voltage. We use the MOSFET all the way on or all the way off, and we use it to switch loads. Now, a complication is there's two kinds of MOSFETs. This is an N MOSFET, this is a P MOSFET. And the difference between them is if this is a load, like say it's a motor or a light, the N MOSFET goes to ground, and it's a sink of current. It takes current out of the load. The P MOSFET goes to the power supply, and it's a source of current. So the P MOSFET goes above your load, the N MOSFET goes below your load, and we'll have use cases for both of them. But that's the component we use to switch current, and a tiny MOSFET can switch a huge current. And so with that, you can drive speakers, drive motors, drive bright lights, all sorts of things. Okay, so that's MOSFETs. You can use batteries, of course, you're familiar with that. We try to avoid batteries, non-rechargeable batteries, so we don't want to create waste. Regulators, this is an example of a regulator. What the regulator does is, on one side, you put in a range of voltages. And so this regulator is, this one is spec'd for 5-volt output, and the input can go up to 30 volts. Then the regulator goes to ground, and on the output, there's always an output capacitor that you need. You can optionally put one on the input. And so this goes up to 30 volts here, but it always puts out 5 volts here. So the regulator takes a varying voltage and gives you a fixed voltage output. And so, for example, many of the processors we use run at 3.3 volts, but the USB gives you 5 volts. And so we use the regulator to go from 5 to 3.3. Now, the regulator is inefficient, and I'll talk about that in a moment when I get to power. And so there are what are called DC-DC converters that can be much more efficient if you reach a limit of just the regulator itself getting hot. Op-amps, it makes me sad you'll probably never touch one, because they're beautiful parts with amazing performance as amplifiers, but we don't use much of them anymore because they're built into the microcontrollers already for low-level signals, and for high-level signals, we switch switch the MOSFETs. So you probably won't see op-amps. Then we get to the microcontrollers, and so we spent a few weeks starting to learn about them, and we have a few more weeks of input and output devices and networking to learn much more about what's going on inside the microcontrollers. And then I won't talk today, but in a few weeks, I'm going to cover lots of sensor components. And next week, I'll cover lots of outputs. So bright LEDs, display screens, speakers, motors, I'll cover in a week. So that's just a tour through components. There's a lot to learn beyond it, but that's just an introduction to the components. So then now with components, we need to make circuits. So once again, you should all have a copy of Art of Electronics in your lab. It's a wonderful Bible that's just full of all sorts of tips and tricks and insights into everything to do with electronics. Some general principles in circuits design. Kirchhoff's law says all the current going into a node and out of a node adds up to 0, and all the voltages around a circuit adds to 0. There's some important exceptions to that, but those are general principles. And then this is very important to know about. If you have an analog component, there's current flowing through it, and there's a voltage drop across it. And power equals IV. And since I equals from I equals V over R, power equals I squared R. So what that means is the amount of current and the drop of voltage gives you power. Power in turn uses up battery life. It needs a bigger power supply, and it can generate heat, and it can generate substantial amounts of heat. So this can sound abstract, But as you run into this, you can need to put heat sinks on components to help them cool. You can need to change component families to reduce dissipation. You can need to move to bigger batteries or bigger power supplies. And so this might control how long a sensor lasts in the wild. And so power is going to be a very important thing to be aware of. At the end of today, I'm going to talk about test equipment. And one of the things I want you to do is actually measure power consumption in your devices to start learning about that. So now we get to EDA. EDA is electronic design automation, and that's the general term for designing electronics. And the reason we need a special term is, in theory, you could use any of the tools we covered, but when you design a circuit, you might start by sketching, then you make a schematic of how the components are connected to each other. Then you have to place the components for where they go on the board. You need to route how the traces go on the board, travel on the board. If it's a non-trivial circuit, you simulate it, and then you need to produce fabrication output. Then there are a lot of details. So there's the layers. We saw this in the PCB week of the numbers of layers in a PCB. You need to keep track of the layers. There are the vias go between top and bottom. You can have planes that you use to distribute power. You can have areas you fill, for example, with ground is one of the jobs. And then there are the design rules. And so this is a board house, and this gives you the design rules for the board house. So this is how skinny can a trace be, how close together can a trace be, how small can a hole be. There's a whole series of design rules. Similarly, if you're going to fabricate it in-house, it's related to the tooling you're using. And so for a non-trivial board, you need to do a design rule check, which is, can you fabricate it? And you need to do an electrical rule check, which is does the board actually reflect the circuit you designed? And so all of that is so specialized. That's where there are these tools. So to start, this was a student who was a good artist, and he did the design assignment, but then for fun, he redid it by hand. So he just, by eye, looked at the components and he made a drawing of the circuit. He scanned it and fabricated it. Beautiful thing to do, very expressive, no design tool, no editing. You can do it. I don't recommend it. In the early days, we used to do circuit boards with tape. We would actually physically tape it up, and then we would take a picture and etch it. We don't do that anymore. Then these are really fun things I recommend. So Tinkercad gives you a virtual breadboard and components, and you can assemble them and simulate it. Virtual breadboard is another version of a virtual breadboard. And fritzing, let's see, is another version of a virtual design environment. And so all of these let you, rather than doing it physically, let you design circuits in a kind of a CAD-like environment and then run them and simulate them. I don't recommend them for serious design work. There's a limit to the complexity, but I do recommend them. They're really fun for learning. So then I'll skip up to KiCAD. So, and Eagle. So if you're using Fusion, Eagle has a complex lineage. It went through a few different owners, But now Eagle is built into Fusion. So Eagle is a powerful EDA tool, and it lets you do the design work right in the Fusion environment, really nicely integrated. So if you're in Fusion, Eagle is a good choice. And then we come to KiCAD. So KiCAD is not from, but connected to CERN, the particle accelerator. It's open source and cross-platform. It started as a series of separate programs and was cumbersome to use. But all of the separate programs have been merged together nicely, and KiCAD has matured into a wonderful EDA tool. So KiCAD is open source, freely available, cross-platform, and I strongly recommend it. So I'm going to spend a while on this example. So here I am running KiCAD 8, the current version. And I typically use Linux, so I'm doing this in Ubuntu. So I'm going to start up KiCAD. In KiCAD, I'm going to talk much more about libraries. Let's see. In Pablo's linking, is this Adafruit tutorial?
Yep, that's my level.
Okay. Okay, good. I'll make a note to add that. Okay, so here I am in KiCAD. In a little bit, I'm going to talk about the libraries. Libraries are where the tool learns about the components. So one of the things you need to do is tell it where to find symbols and footprints. A symbol is for the schematic. The footprint is for what goes on the board. It has many built in, but then they're great sources of them. So this is a Fab library. And again, I'm going to give you these links shortly. Chris helps maintain this. And then this is one of a few sites that are really handy where you can type in a part to the site. So here's one of our microcontrollers. And then it'll, from it, it'll look up where you can buy it, but it'll show you the schematic symbol, the footprint, and the 3D package. And then you can download all of those. So now in KiCAD, I'm going to start a project. And so this will be a demo project. And it just made two files for me. One is the schematic and one is the PCB. So I'm going to open the schematic. Then I'm going to start a tool. And I use this tool to add components. And there are many available. So I'm going to start searching. I'm going to search for the Tiny 412, one of the nice little processors. And so it's pulled up the schematic symbol and a package for it. So I'm going to put that in my schematic. So there it is. Now I'm going to just add one component for demonstration. I'm going to add a resistor. I can pick which kind of resistor. So there's my resistor. Now I'm going to start wiring them. So I pick the wiring tool. And so I'm connecting them to the pins I want to use. So I've done something sort of nonsensical, but a simple example. I've connected a resistor to a microcontroller. Now the next thing is I'm going to go to a tool for footprints. So it already knows what kind of microcontroller, but the resistor can come in many different packages. So I'm going to say I want a 1206 package, and then I'll pick the 1206 package for that. So I tell it which package. Now I'm going to go to the PCB tool. So I'm going to, I just asked to import from the schematic. So now what it's showing me is there are my footprints, the parts I'm placing, and they're connected by what's called a rat's nest. which is all of the wires going between them. And so initially, you can barely see them. It's clearer when you're doing it. You see those lines. Now what I'm doing is I'm rotating the component. I'm placing the component at a convenient location, and then I'm rotating it to a good orientation for where I want to connect it. So now I've placed the components, and KiCAD actually has a tool to help you with that. It can analyze the rat's nest, and you can ask it to give you a starting placement of the components, and then you can edit it. If you place them poorly, it's hard to route. If you place them well, it's easy to route, and it's easy to design with the connectors you need. Okay, so now I need to route the traces, and then here it has a bunch of options. What I'm showing here is when you route, it can tell you if you collide, it can pull the traces around things in the way, or it can do a nice thing called shove routing, where you actually push traces out of the way. So that's what I'll pick here. I'm going to pick the routing tool. And now what I do is I start clicking for where I want the wire to go on the board. So that's a pretty easy one to route. I'll go from there to there. Now, that was so easy, you can automate it. So now what I'm going to do next is I'll pick a pad, but rather than me doing it, there's a whole bunch. Actually, I'll add a link to this is a link to KiCAD shortcuts. And there are all these things, just single letter commands you can type as you get more comfortable with it. And so I'm going to type the letter F. And as soon as I type it, boop, it just happened. As soon as I type it, it routed the trace for me. And it's interactive. You can start routing, and then you can tell it to finish. And then when I did it, there's something subtle happening, which is you can't quite see it in the video, but when you use it, you'll see zoomed in. Each of the pads and traces has a boundary around it, which is your design rule clearance. That's how close you can come. And so when it routes the trace, it does it with staying outside of those boundaries. Full auto routing routes all the traces, and that's a hard problem. You need it on really big boards. On small boards, typically you can do better than the auto router. But it's very handy to have the interactive tool that just as you begin routing, collaborates with you to route the traces. Okay, so for this simple circuit, we've routed the traces. Now on the right are all of the layers. And so there's copper on top, there can be copper on the bottom. I'm going to go to what's called edge cuts, which is the boundary of the board. So now I'm going to pick a rectangle tool. And now this is the physical size of the board. Now, once I did that, a neat thing has happened. Right away, I can open a 3D viewer. And so magically that appeared. Because KiCAD, the footprints come with 3D, most of them come with 3D models. At the same time I was designing it, I was actually doing 3D design. So I've got this 3D rendering, but it's better than a 3D rendering. You can export this as a step file, and you can bring that in your CAD environment so that you can design how the electronics fit into your system using the actual CAD for the electronics. And as soon as I design the PCB, right away I have that. Okay, now I need to make the board. So if you send it to a board house, universally they take Gerber files. And so the fabrication output lets you send out Gerber files. But in addition, you can export other formats. And for in-house prototyping, you can export SVG. So I'm going to go to the SVG export. I'm picking the layers I want. I want the copper on top. I want to know the boundary. and I want it just for the board. And so I'm going to export the those two layers. Then if I go to mods, I can take the SVG import in mods. I'm going to bring in the copper. Right now it's inverted. In mods, think of light is high and dark is low. And remember, we're offsetting for the tool. And so if I do this, it's going to cut inside the traces, which I don't want. So I'm going to invert it. Now it's going to cut outside the traces. And so that's ready for me to machine. And then I'll bring in the exterior. And so now it'll cut around that. Now, there's one minor detail. It's cutting on the inside of the line. And so the actual size is going to be offset by the tool diameter. So it's slightly smaller than what I did in the edge cuts layer. If you want that to be exact, you can make a new layer on the inside that accounts for that offset. But now I've exported the traces and the board perimeter, and I've sent that into SVG, and that's ready to machine. So those were all of the steps. Almost all of the steps I showed you here. I laid out a schematic. I picked where to place the components. I routed it. I skipped the simulation, which I'll talk about, and I produced the fabrication output. So I strongly recommend KiCAD. It's freely available, cross-platform, powerful, all sorts of benefits. Yeah, Megan is noting an example that she did. And in fact, let me see, in the prep meeting, let's see, I'm looking where Hank, sorry, Hank, Hank, can you put in the chat again that crazy link you showed? Let's see, I don't think I kept that. Yeah, if you can put that in the chat again. I'll show that when you can add that. So all of that's doing all of these steps in KiCAD. Beyond KiCAD, Altium is a high-end commercial tool. They have an entry-level one, circuit maker. Then OrCAD is a high-end tool. Cadence and Synopsys Mentor are then tools that go from PCB design all the way into IC design. See, thank you, Hank. Let me save this in my notes. And let me go here. So this was just a beautiful project where somebody went from KiCAD all the way into Blender, making a beautiful so this was using, this is a crazy mashup. This is using the automation in GitLab to go from KiCAD into Blender. And see, Megan is showing designing this board in KiCAD and then sending it out. And then I'll come to that in assignments. That's going to be one of the group assignments. I'm going to mention these just in passing. Magic and K layout are open tools for integrated circuit design. And slowly emerging are accessible fab houses for doing custom ICs, still not quite ready for a class like this. So libraries. Designing electronics is all about the libraries. Oh, right. lots of links for me to add this week. KiCAD produces step that goes into your favorite CAD tool. This is in particular a FreeCAD workbench designed to much more closely connect KiCAD and FreeCAD so they can talk to each other. I'll add that one also. So EDA is all about the libraries. This is a link to a number of different libraries for Fab Labs. And the most active one is the KiCAD one that Chris has been doing a good job of helping to maintain. Now, slowly, personal libraries. So you'll likely, so KiCAD has many libraries. You can right away start with the Fab library. Sorry, I did that too quickly. If you go to KiCAD, these then are Fab libraries you can download of symbols and packages. But I'd show that in the video. These sites like Snap EDA let you take any component, pick the component, and then they'll give you the footprint, the schematic symbol, and the 3D model. Actually, this is an interesting example. It happens, I'm surprised they didn't have the exact symbol for that one, but you can ask them for it. And what makes that work is these sites help sell components. So the component vendors help support the sites to do it. And so with these tools, you can easily pull in libraries for components you want to use. So next is simulation. Analog simulation is the underlying physics. Digital simulation isn't physics, it's just logic, which if you're simulating a microprocessor, you typically don't need to go down to the physics. And mixed signal is combining both of those for things like digital and analog. SPICE is ancient, came from Berkeley a long time ago and has lived on and is still very heavily used. There are many different versions of SPICE that are freely available. So NG-SPICE, for example, is one of them. And then one of the really nice things is they're now built into the packages. So KiCAD knows how to talk to SPICE. And so once you design your circuit, right in that environment, you can run the simulator and see what the circuit's going to do. And so I didn't mention, but at the same time, you're getting the footprints and the schematics. Excuse me. The libraries also increasingly have the SPICE models for the components. Likewise, this is the connection between Eagle and SPICE. And so both of these let you work in the design environment, but simulate. Then SPICE is ancient. Let's see, Ulu likes LT SPICE. And yeah, the vendors help support these because they help you use their parts. In addition to those simulators, there's a number of more recent simulators. And then one of my favorite ones is, this is just a really fun one, Falstad. And I don't know who Falstad is. In fact, I'd love to meet Falstad. There's a vast sea of circuits. Like, I was talking to start about a MOSFET. So here's a simple MOSFET circuit. Then once we have a MOSFET, you can connect two of those and you can make what's called a CMOS stage. And then from there, we can make more complex MOSFET circuits. 555 is a fun little chip. that has a long history. This is simulating it oscillating. There's just this huge range of, oh, let's see, this is, when you go from analog to digital, delta sigma is one kind of ADC. And this is a classic mixed signal simulation that mixes analog components and digital logic. And so that's a really fun site for playing with simulating your circuits. Okay. Next is HDLs. So when you design a billion transistor chip, you don't do it by clicking a billion times. So Verilog, ooh, that looks like it's broken. I'll fix. Verilog and VHDL are the languages you use to design circuits. Let's see. Zaid has added one I don't recognize. Oh, this is another simulation site. Okay. Interesting. Okay, so when you design an integrated circuit, these are the language, you use hardware description languages. And then for many years, I've used HDLs to do circuit boards. And so many of the examples I'll give you, if we take, let's take a D21. Here's a PCB, but I've written it in a hardware description language, which I'll show you in a second. And that's less intuitive when you start, but what makes it powerful is you don't need to, you can express all sorts of programmatic relationships that are hard to do with the GUI. And from the HDL, you can produce all sorts of outputs, like this is producing Gerber for PCBs. And so here's an example of that. So in here, here's a renderer, here's the hardware description language, here's an interpreter. And then I'm going to first edit the file, and I can tell it what I want it to produce. So it's not a separate output menu, just the file knows how to do all the different layers of the board. And then to edit it, I'm going to add a component. And rather than clicking and dragging, I say I want it under the crystal and next to the connector. And what that means is later, if I move the crystal or the connector, these know their relationship, and so they move together. Then I'm going to do some wires. And rather than clicking and dragging, I say I want the wire to go from the connector to the resistor, and I want the resistor to go to the pad. And then if I rearrange things, they automatically rearrange because they know what they're supposed to be connected to. And so you can express sort of how you're thinking about the design in ways that are hard to do by clicking and dragging in a GUI tool. So many of the examples I'll use, let's see, well, let's come to AI at the end. Many of the examples I use are going to use that. I don't recommend this because that spawned this. Let's see, Francisco, you need to mute. SV, this is a paper on a project done by Quentin, Fab Academy instructor Leo and Nadia. And this is really fun. This was inspired by what I showed you, but now just runs in a browser. And so they took all of my examples, imported them. And so in this environment, you can move components around in the GUI. So for example, if I move the regulator, you'll see how its capacitor moves. You can take components from a library and you can drag them into here. And then what's happening over on this side is, if I move that over, this is the hardware description language. And so each time I change a component over here, it changes over here. And so I can take the, I can edit the, let's see, I'm not sure. That's interacting in a funny way. I'm not sure what that was doing. But I can edit the hardware description language like I showed you, and I can do it in the GUI, and you can go back and forth between them. So SVG PCB is an interesting, yep.
There was a direct connection from SVG PCB to the mods.
Oh, that's right. They added that. I should note that. So so once you're in SVG PCB, again, yeah, I don't know what that was doing before, but now I can do this here. I can get in, I can edit the components by number, I can edit the components by GUI, and I can do all of the sort of relationships. So the graph makes the program and the program makes the graph and they stay connected. And then when you're done, SVG PCB knows how to talk to multiple things, including it knows how to talk directly to mods. Miriam's great art. So if I pick a machine, let's see, I haven't seen this version. Oh, look at that. So SVG PCB just opened mods, putting my design right into it. I'll make a note, SVG PCB mods. So on the one hand, I love SVG PCB. Nothing to install, it all runs in a browser. The web page auto documents, and it lets you do both graphical and hardware description language programming. On the other hand, SVG PCB can't do all the things I showed KiCAD can do. It can't yet do push routing. It can't do auto routing. It can't yet export 3D CAD. So those may come in the future. I'm making more use of KiCAD than I used to. Oh, let's see. Chris says you can export to KiCAD. You can export in what format? The Gerber into KiCAD? Or
Well, it's just it's just the footprints for now.
okay, yeah, just
so
the
footprints and traces, and then you can open it up in KiCAD, and then you can use all the KiCAD functionality to edit the design manually if you need to.
I see. So, let's see. Oh, I see. Okay, sorry, I'd missed that. So it's making a native KiCAD file.
Yeah.
Got it. Okay. I missed that also. Okay, very interesting. So this is a great starting tool. It has plenty of functionality on the scale of this class, and it's continuing to be developed. So you could do everything we're going to do with that, but I would still learn a tool like KiCAD that can do the things beyond what you can do in SVG PCB. And then finally, KitSpace is one platform for sharing electronics. Okay, last topic is going to be test equipment, but first for the individual assignment, I want you to use an EDA tool. So KiCAD, Eagle, SVG, PCB. In the last few electronics weeks, you've been using a microcontroller development board. I want you now to develop one. So it should have a microcontroller. It should be able to interact and communicate. And you can make a general purpose one, or you can particularly design it around your final project. And then at this point, you should now be comfortable making and assembling electronics. So design the board, make the board, and wake it up and see that it works. And then extra credit is try another design workflow. Another extra credit is export CAD and design a package for it. And another extra credit is simulate it. Now, for the group assignments, yeah, let's see. Ricardo is noting Pindi is the site where you can sell your electronics. For the group assignment, I want to talk about test equipment. So thanks to our friends in Shenzhen, these are quite commodified, and there are these cute little ones. So this is a little power supply, and it lets you set current and it picks voltage. You pick voltage, it picks current, and it measures how much current or voltage you're providing. Let's see, that one was broken, the multimeter. I'll fix that link. Then there are these cute little pocket oscilloscopes that are about $100. So this shows you the the analog signals versus time. Then there are logic analyzers that show you digital signals versus time. And then you can get tools like these. This is a bench scope, and it can show you the waveforms, but it can also interpret them. And so, for example, for I2C or for serial, it can actually analyze them and interpret them. Then this is a powerful tool that takes the digital signals, runs on your computer, and it knows all of the protocols, and it can take big data traces and can find what's happening in them. And there are a number of very inexpensive knockoffs of those. Nicholas is noting two interesting projects I haven't heard of. Scopy. And SIGROC, which looks like fun with RP2040s. Interesting. Interesting. Yeah, I'll look at these. I wasn't aware of these. So those are using those. And let's see, I don't know, Yanni, if this is current. A while back, Yanni had done Fab Measure, which is fabbable test equipment.
Yeah, I mean, we have a couple of equipments I haven't updated yet. I must need to remember to do that. And if anyone is making any measurement devices or electronic or any other, please let me know and I will link them into that site.
Okay. And just these links Nicholas just put in look interesting, and we should test, but probably worth linking to. So the group assignment is to observe operation. And so to understand that, let's say here's a host computer. It's talking over USB to your microcontroller board. And then from here, you're, say, running over I2C, and you're talking to a display, and then you have this connected to a power supply and ground. So one of the things you can do is with a logic analyzer, you can connect it to the USB. You can see the raw digital signaling, And then the logic analyzers can then parse them and tell you what the messages are. Then if you use a analog scope to look at it, what you will actually see is instead of a sharp transition, you'll see some ringing and some overshooting and stuff like that. And you can see eventually when that gets bad enough, you have trouble with the signals. And so in turn, if you connect a analog scope to your power supply, what should be a clean power supply, you might see when, for example, a power transistor switches, you'll see big surges of noise on the power supply. And then one of the most important things to do is to measure the power consumption. So if this is your device, if you use a smart power supply, the device itself will measure the power going in. If you put a tiny resistor, like a 1 ohm resistor going to ground, you can measure the power coming out. If you're using a USB powered device, there's a great category now of, and I'm going to talk more about this next week, USB power meter. USB supplies increasingly let you make lots of volts and current conveniently, and then these devices let you measure what's actually flowing through the USB. And so for the group assignment, I want you to see what the actual signals look like. See, Adrian is linking his documentation on using a logic analyzer. Good. And the last part of the group assignment, and this one is suggested for this week, but I just want you to do it at some point in the cycle, is now that you're designing PCBs, pick a PCB that's hard to fabricate in-house and go through the steps of producing the Gerber and sending it to a board house. You don't need to do that for everybody's boards, but I want you to see how to do that as a group. So stepping back, like many weeks, this is a lot to learn. This was a tour through the components. You won't master them right away. And then this was an intro to all the things you do in EDA. You won't master that right away. But this week, you should be able to get started with one of the EDA tools, design a basic board, and fabricate it. And then in the coming weeks, we'll go in much more detail about each of these steps and unpack them. So in input devices, we'll look at all kinds of analog signals and digital signals. In output, we'll look at handling high voltages and high current. Let's see, Ricardo, you're showing an example of debugging. Oh yeah, this is nice. So he's getting problems in his I2C, and then the logic analyzer is okay. This is a really good. This is a really good debugging example. Nice. Okay, finally, let me add with a few examples. So this was Adrian, who designed a board, and then he designed a whole family of peripherals for the board. And this was the inspiration for what became the Quintoris. Second is your boards don't have to be rectangular. This was one of my favorites. This was Annie's. Annie made me as a PCB. The PCBs can be expressive. And then the third example was, for those of you who are comfortable programming, Kai did something crazy this week. For routing his board, he wrote his own smushy algorithm. So he wrote his own tool where he laid it out, and then I love these, was able to let the whole board kind of smush and deform, not as picking a fancy CAD package, but just he wrote his own code for that. So that's part of the inspiration that led to SVG PCB. And if you get excited, you can learn from his example and you can play with the workflows. You know, in the end, we're producing artwork for fabrication. As long as you can do all the things I'm describing, any of these tools are fine. Oh, let's see. Chris has the Tarantino. So what's different in the Tarantino, Chris?
Oh, it has some more features. So I wanted to demonstrate different drill sizes. I wanted to demonstrate a double-sided process.
Okay.
And also engraving process, so that you can engrave images on the other side.
Nice. Okay. And Miriam's put in the chat another really fun board design. So your board designs can be expressive. Yeah, Nicholas is noting, and I strongly agree, it'd be nice to have an AVR version of these universal boards. So as usual, don't worry, be happy, meaning you won't master all the components this week. You won't master all of EDA this week. The goal is to get you started with the design workflow, design your first board from scratch, and fabricate it. And then we'll spiral and add more and more features. Okay, that's electronics design. Open time Saturday as usual. Use that for any question and answer. I started a hydrogen issue, use issue trackers and Mattermost to discuss projects. And then next week we'll cover displays, speakers, motors, and that'll lead into machine building recitation, and that'll lead into the machine building assignment. Okay, happy designing. See you in a week. Bye-bye.
Hey.
Thank you.
Ciao, ciao.
Bye bye.
Bye bye.
Bye.